Build a multi-flow sheet liquefied natural gas plant model. In this video, we'll complete a multi-flow sheet model for the simulation of LNG production. The video will provide an opportunity to apply multiple sub-flow sheets to a fully integrated process simulation. Liquefied natural gas production started in 1960s. It can be applied as fuel for motor vehicles, for residential use, and for industrial consumption. A typical energy production model includes the following process areas: acid gas removal, dehydration, propane refrigeration, pre-cooling train, a compression section, and the final liquefied natural gas production train. Any further process specifications such as the control of the refrigerant flow rate can be added as well. This video includes the following tasks. Task 1. Define the properties environment. Task 2. Acid gas removal and dehydration. Task 3. Pre-cooling train. Task 4. Convert natural gas to LNG. Task 5. Compressor train section. Task 6. Refrigerant temperature control. Task 1. Define the properties environment. When natural gas is cooled to a temperature approximately minus 160 degrees centigrade at atmospheric pressure, it condenses a liquid called LNG. Natural gas is composed primarily of methane, typically more than 70%, as well as ethane, propane, and other hydrocarbons. Impurities such as nitrogen, oxygen, carbon dioxide, sulfur compounds, and water are also present. Given these described species and the process conditions, the LNG process model could utilize the Bingo-Brasser equation of state as its property package. This would be sufficient for most preliminary type models. The BRSFE method may be more suitable for rigorous model, but this would have to be verified for each individual simulation. SRK may also be employed, but the low temperature operating condition may be outside the acceptable range of SRK. Here is the operating boundary for the Bingo-Brasser and SRK methods. Start a new case. Add the following components. Now navigate to the fluid package form. Click Add. Select Bingo-Brasser. Now that you have defined your components and property package, you may begin working with your flow sheet. Click the Simulation Environment button to continue. As we highlighted before, the LNG process model includes the following units: acid gas removal, dehydration, propane pre-cooling train, compressor train, and LNG section. These units will be modeled in Aspen hysys using the sub-flow sheet operation. Each sub-flow sheet will then contain the unit operations that comprise that unit. We will begin by building the structure of the overall flow sheet using sub-flow sheet operations. Add a material stream. Name it feed gas. Set the temperature to 38 degrees centigrade and set the pressure to 4,200 kilopascal. Set the mass flow to 386,700 kilogram per hour. Go to composition. Enter the following composition. Note that the feed gas stream is defined on a dry basis with no water. It needs to be saturated with water for the purposes of the dehydration step of the LNG process. Add a saturated unit operation. Name the product stream saturated gas. The saturated unit operation hasn't converged for the wet bulk calculation, but this won't affect the calculations the saturation we need for this flow sheet. This concludes the first task of our video. Task 2. Acid gas removal and dehydration. The first stage of the LNG process flow sheet will be to remove the acid gas components and then dehydrate the gas. This is an important first step, as removing the acid gas components will make the natural gas stream far less corrosive. Removing water will prevent the formation of hydrates, which could otherwise clog piping and equipment and cause other operational hazards. In this process model, the gas sweetening and dehydration units will be simplified by making use of the hysys component splitter operation. A more rigorous approach would be to build 4 process models for gas sweetening and dehydration. For an example dehydration unit, refer to the gas dehydration with thick process built in an earlier video. Add a standard sub-flow sheet to your flow sheet. Click Start with a blank flow sheet. Change the name to natural gas purification. On the inlet component to the sub-flow sheet, select the external stream saturated gas. Click Sub-flow sheet environment. Add a component splitter inside the sub-flow sheet. Name it gas sweetening. Name the overhead outlet sweet gas. And the bottom outlet waste. Navigate to the parameters page. Set the sweet gas temperature to 38 and pressure to 4150 kilopascal. Set the temperature of the waste to 20 and the pressure to 101.3 kilopascal. Keep the rest to default. Now navigate to the splits page. Set H2S and CO2 to 0.001 for both of them. Set other components to 1. We got a consistency error because we forgot to name an energy stream. Now the splitter has solved. Add another component splitter operation to represent a mold sieve unit that would remove water and thus dehydrate the natural gas. Name it mold sieves. Name the overhead outlet natural gas feed. And name the bottom outlets H2 waste. Name the energy stream Q mode saved. Go to the parameters page. Set the natural gas feed temperature to 25 and pressure to 5000 kilopascal. Set the H2O waste temperature to 20 and pressure to 101.3 kilopascal. Go to the splits page. Set H2O to 0 and other components to 1. Now the receive component splitter has solved. Go back to the main flow sheet. On the outlet connections to subflow sheet, name the external stream connected to the internal stream of natural gas feed as well. Elect the transfer basis stack. For the material stream, saturated gas, waste, and natural gas feed, set the transfer basis as TP flash. This will hold temperature and pressure constant at the material streams flow between subflow sheets and the main flow sheet. This concludes the second task in this video. Task 3. Pre-cooling tray. After the natural gas stream has been dehydrated and sweetened, it can be fed to a pre-cooling tray. This tray will be modeled as a series of hysys cooler operations to successfully lower the temperature of the stream. A parallel cooling tray is also created to handle the mixed refrigerant coolant. This mixed refrigerant coolant will be used further downstream in the process to help generate the LNG product. Add a material stream to your flow sheet. Name it MR-Cool. Set the temperature to 32 degrees centigrade and set the mass flow to 1,400,000. Go to composition. Enter the following composition. The MR cool pressure is still unknown. This will fill in later on as this process is built. Add another subflow sheet. Click Start with a blank. Change the name to pre-cooling tray. Set natural gas feed and MR cool as outlet connections to the subflow sheet. Select the transfer basis tab. Change the transfer basis of the natural gas feed to BT flash. Click subflow sheet environment. The cooling trays for the natural gas mixed refrigerant will be constructed using the hysys cooler operation. For the purpose of simplicity, each cooler will reduce the temperature of each process stream by a certain amount. For a more detailed model, you could use the hysys heat exchanger operation instead. Add a cooler. Change the name Set the L stream, name the energy stream, name the outlet stream, set the delta P, set the outlet stream temperature, complete the pre-cooling segment for the natural gas by adding 2 additional cooler operations. Use the same delta P for chiller 2 and the chiller 3. And set the temperature of 31 stream minus 15.15 and the temperature of the 2 LNG section to minus 35.15 degrees centigrade. The natural gas stream is now fully soaked and defined. The next step will be to add 3 coolers for the mixed refrigerant side. Set the delta B for each cooler to 5 kilopascal. Set the temperature of the stream 32 to 4.8 degrees centigrade and the temperature of the stream 33 to minus 15.15 degrees centigrade, and finally the temperature of the MR cold stream to minus 35.15. Now go back to the main flow sheet. Create 2 outlet connections, sub-flow sheet for the 2 LNG section and the MR cooled internal stream. Title these new streams with the same names, as you can see. Make sure that the transfer bases for both streams are pH flash. Now set the pressure of the MR cooled stream. Enter a value of 3,218 kilopascal. This concludes the third task in our video. Task 4. Convert natural gas to LNG. After the pre-cooling stage, the natural gas stream is ready for conversion to liquefied natural gas. Mixed refrigerant, dropped down to low pressure and temperature, will be utilized as the cooling utility for the natural gas stream. The main heat transfer operation in this portion of the process will be the LNG exchanger, rather than the semi-cooled cooler model utilized in the pre-cooling train sub-flow sheet. At sub-flow sheet, assign the 2 LNG section and MR cooled material streams as inlet connections to the sub-flow sheet. Ensure that the transfer basis for both inlets is assigned as pH flash. Enter the sub-flow sheet الغاز. Add a separator. Set MR cooled as an inlet stream. Adjust the name. Name the vapor outlet and the liquid outlet. Add a material stream and name it 20. Then Don't define any conditions for this stream as it will become calculated. Add an LNG exchanger. Please note that the LNG exchanger allows for multiple hot and cold streams to pass through the operation. The operation solves heat and material balances based on a variety of allowable thermal specifications, such as heat leak and heat loss, UA values, or temperature approaches. List the streams 14, 15, 20, and 2 LNG section as an streams. Create outlet streams. Make the flow to LNG section at 3, 14 to 16, 15 to 18 hot, and the last stream 20 to 9 cold. Pressure drop also needs to be defined for each stream, the LNG exchanger. Set a 200 kilopascal pressure drop for all hot streams. Set a 30 kilopascal pressure drop for the cold stream. Select the worksheet tab. Enter a stream temperature minus 87.15 degrees centigrade for stream 16. Define the same temperature for stream 18 and 3. The LNG exchanger is still not yet solved, as the stream information for stream 20 and stream 9 are still unknown. However, you will continue to build the LNG process flow sheet, and these streams will become calculated later. Add a valve. Set the stream 18 as the L stream to the valve. Adjust the name. Name the outlet stream 19. On the worksheet tab, set the pressure of stream 19 to 260 kilopascal. A mixer will be added to mix the low pressure, low temperature stream 19 with another very cold stream from the second LNG heat exchanger. These two are combined to form the current cold inlet to the first LNG heat exchanger, stream 20. Add a mixer. just the name. Keep the default automatic pressure assignment. Add a separator. Set the outlet stream to stream 16. Name the vapor outlet 21 and the liquid outlet 22. Now the simulation is ready for the second LNG exchanger. Set the inlet streams. Set the outlet streams. Set the flow 21 to 23 as hot and 22 to 25 as hot as well, and 27 to 17 as cold, and 3 to 4 as hot. Set the hot side pressure drop to 200 kilopascal. And the cold side to 30 kilopascal. On the worksheet tab, set the temperatures of streams 23 and 25 and 4 to minus 113.7 degrees centigrade. Add a valve. Name the outlet stream 26. Set the pressure of stream 26 to 260 kilopascal. Adjust the valve name. Continue by adding another mixer operation. Connect the stream 27 to the outlet. And the 24, 26 to the outlet. Adjust the mixer name. Add the third LNG heat exchanger. Adjust the name. Set the L streams. Set the out streams. Keep the default hot and cold configuration. On the worksheet tab, set the temperature of streams 28 and 5 to minus 155.8 degrees centigrade. Now add a valve. Connect the stream 28 to the inlet and 29 to the outlet. Enter a pressure of 260 kilopascal for stream 28. We forget to set the pressure drop for the third LNG heat exchanger. Set the hot side pressure drop to 200 kilopascal and the cold side pressure drop to 30 kilopascal. The three LNG heat exchanger and the subflow sheet have calculated at this point. The last step is to drop the pressure of the LNG stream and separate out the desired liquid product. You will add a valve operation followed by a regular separator to achieve the final product. Add the final valve and separator. Just the valve name. Set the L stream and set the outlet stream. Name the vapor out stream to flare. And the liquid out stream LNG product. Go back to the main flow sheet. On the Connections tab, enter LNG product and to flare as external stream connections to the outlet of the subflow sheet. Also create an external outlet stream for stream 9, but name the external stream MR return. This concludes task 4 in this video. Task 5, compressor drain section. The only remaining gap in the LNG process you have built is for the compression of the mixed refrigerant fluid. The mixed refrigerant MR return stream leaves the LNG section at low pressure and needs to be boosted up to high pressure for when it returns to the pre-cooling trip. 3 stages of compression will be used in this final subflow sheet along with a few aftercoolers to control the temperature of the refrigerant. add a blank subflow sheet. Name the subflow sheet compressor trail section. Add MR return as an inlet connection to the flow sheet, to the subflow sheet, and MR cool as an outlet connection. Click the transfer pieces and verify that both connections are set for a pH flash. Click subflow sheet environment. Add a compressor unit operation with outlet pressure 550 kPa. Add a cooler operation with pressure drop 20 kPa and outlet stream 20 degrees centigrade. At the second stage, compressor and cooler. Set the outlet pressure of the outlet of the second compressor to 2600 kPa and the pressure drop of the cooler to 20 kPa. And finally, the temperature of stream 11 to 104 degrees centigrade. Now add the third stage of compression, making the outlet stream MR cooler. Don't forget to set the pressure drop of the third cooler to 20 kPa. This concludes the task 5 of this video. Task 6, refrigerant temperature control. Even though the structure of the LNG plant model has been completed, we can still add additional functionality to control desired process conditions. The most convenient way to do this in Aspen hysys is to use the adjust operation. In this final task of the video, you would add an adjust operation to define the temperature of the mixed refrigerant stream as it exits the LNG section of the process. Now add adjust operation to your flow sheet. For the adjusted variable, select MR cool stream and select mass flow variable. For the target variable, select MR return stream and select the temperature variable. Enter a value minus 48.15 degrees centigrade. Click the parameters tab. Set the maximum iteration to 100. Enter a minimum value of 100,000 kg per hour. And a maximum value of 3 million kg per hour. This concludes the last task of our video. Thank you for watching.